Hello and welcome, and this lecture we are going to look at independence. Okay, when do we say two events are independent? When do we say multiple events are independent? What is the meaning of independence? Well, there's lots of meanings of the word independence in English, but in probability theory, independence has a very specific, well-defined meaning, and quite often people make this mistake of using their intuition. And when somebody asks you, are these two independent, and as a probability question, the people just tend to use their intuition and say, yeah, this should be independent, that should be independent. It's good to have that kind of intuition, but the way probability independence is defined in probability is very precise. It's a very precise, exact definition, and you should also learn the discipline when somebody asks you a question about independence to take a piece of paper, write down a couple of statements, check the precise definition, whether it makes sense, whether it's meaningful or not, and then you accept your intuition whether of being independent or not. Okay, so this is important. I want to stress that once again, because of the normal meaning of the word independence. A lot of people get misled and go into the wrong conclusion very quickly. Remember, there is a precise definition. You always have to check that definition. Okay, so let's go ahead and see what it is. Here's the definition. Start with the definition. Independence of two events. There are two events A and B in a sample space, and when do we say they are independent? Here's the definition. This is the only way you can say two events are independent. Probability of A intersect B has to be equal to probability of A into probability of B. That's it. There's no other intuitive way in which you can define independence. There's no other definition. This is the definition. Two events are independent, A and B, if probability of A intersect B equals probability of A into probability of B times probability of B. The product of the two probabilities should be equal to the probability of the intersection. Okay. So what's the motivation? Why does it make sense, and why is it very useful, etc., etc.? So I've tried to capture that in the slide, in the points that I've written below the definition. The motivation sort of comes, the word independence, and where that word comes from is from the connection to the conditional probability. Okay. Supposing, let's say, probability of B is positive, right? So if it's positive, then probability of A given B, if A and B are independent, notice if probability of A intersect B equals P of A into P of B, probability of A given B will be what? It's P of A intersect B divided by P of B. So if you divide P of A into P of B by P of B will cancel and you will get P of A. Okay. So the event A is independent conditionally of event B in this sense. Okay. If you are in the original space and you find probability of A, you go into the conditional space with conditioned on B and find probability of A. Probability of A given B, you will get the same answer. Okay. So it's as if the occurrence of B did not influence A in any way. Okay. So that's the idea in this. So we think of this as an independence condition. Okay. So it's A, probability of A is unaffected by B. Okay. So now what is so notice what has happened here. So go back to our initial way in which we started with the axioms and we started playing around with events, and we saw this union and intersection of very, very crucial operations, right? Union is like an OR operation, A or B. Intersection is like an AND operation. We saw in one of the axioms, that's the second point here, you go back to our axiom 2. If two events are mutually exclusive, if they are disjoint, right, A and B are disjoint, then the union of the two events is easy to calculate, right? Probability of A union B is P of A plus P of B. Okay, this is called, some people call it the addition rule, right? So the addition rule of probabilities. When you have two events that you think are mutually exclusive and you want to find the probability that either this or that happened, you can simply add. There's no intersection between them. There's no need to worry about the subtraction of the intersection. Okay. Now what independence is telling you is, you can do probability of intersection of two events, probability of two events happening at the same time for one outcome being favorable to both events A and B, right? You have two events A, B. What's the probability of A and B, event 1 and event 2? You have a multiplicative rule only when the two events are independent. It's extremely important. Just like the addition rule works only when the two events are mutually exclusive, they're disjoint, the multiplication rule for AND will work when the two events are independent. Okay. So a lot of people put it like this, the rule of multiplication and rule of addition is very useful in computing probabilities. Okay. So once again, the definition, I want to remind you, don't assume all events are independent. Okay, a lot of people assume events are independent when they are not. Okay, so events are independent if probability of their intersection equals the probability, the product of the probabilities P of A and P of B. Okay, so that's the definition. Okay, so when I state it like a multiplicative rule, it seems like something you can use, but you should know A and B are independent ahead of time. Only when you know A and B are independent, you can do probability of A into probability of B. Okay, all right. So this is definition. So much for the description. So we're going to see a few examples, and I'll point out some pitfalls and places where I've seen students struggle to understand independence. Let's begin with a very simple example. You toss a coin thrice, right? So there's a coin, pick it up, toss once, it comes back, toss second, it shows up, toss third, shows up, you look at the three outcomes. So intuitively, physically, from a very high level, you see immediately that the first toss and the second toss have to be independent, right? So if you have an event involving the first toss, if you have an event involving the second toss, they better be independent. Otherwise, the natural physical sense of connecting to the experiment is going to be too tough for you, right? You tossed once, you tossed second time. What happened in the first toss and what happened in the second toss better be independent in some sense. Okay, so let's see if that intuition is sort of carried over in the definition, but we'll look at it from a definition point of view. Okay, so we know when you toss a coin thrice, you have a probability space which has a uniform distribution, right? The uniform distribution is over what? Over all the 8 possibilities that can happen. H, 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 T, H, T, H, all of those. Okay, so I'm going to define two events A and B, one for the first toss, another for the second toss. Okay, first toss is heads, that's A. Second toss is heads, that's B. Okay, let's see what the event A is as a subset of the sample space, right? All events are subsets of the sample space. What is the subset of the sample space? It's everything with H in the first place, right? So H, 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 T, H, T, H, H, T, T. What is B? Second toss is heads. You go through the 8 ones and pick out the ones which have H in the second position. H, 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 T, T, H, H, and T, H, T. Now, what is our definition? Our definition involves A intersect B, right? It's a bit complicated. Let's see if that's satisfied. So, what is A intersect B? First toss should be head and second toss should be head, right? So, that should H, 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 T. You can see, you can go through the events here and you can see that that is satisfied, right? Now, you check out the condition of the independence, right? Probability of A intersect B equals 1 by 4. Right, isn't it? Why is it 1 by 4? There are 2 favorable outcomes out of 8, right? 2 out of 8, 1 by 4. And that's equal to half into half, and that's P of A into P of B, isn't it? So we see that A and B are indeed independent, so it's sort of a good definition. The definition is not bad. Where you think it has to be independent, it ends up being independent, no problem. Now what about A and B complement? Okay, that should also be independent, right? So why should that be independent? You think about it. A involves the first toss, B involves the second toss, B complement also involves the second toss. Second toss is tails. First and second should really be independent. I will leave you to check that. A and B complement, are they independent? End up being independent, that's true. So what about first toss is heads and third toss is heads? That should also end up being independent. I'll leave you to check those two. Okay, these two you can check. So once again, I mean, I'll step back and give you that warning. I mean, you have this intuition on what events are going to be independent, but always check with the definition. Make sure that the actual definition holds. Let's look at another event where quite often people get misled. So I put this example right next as an interesting example. Let's say you throw a die, and I'm going to define an event A as the number being even, and the event B as the number being odd. Okay, so people have this wrong intuition that when the two events are disjoint, they become independent for some reason. I mean, it seems like that, right? Sometimes people have this wrong feeling about it, but that's absolutely not true. You can quickly check, right? So even and odd are disjoint. If you do A intersect B, you have the empty set, and what's probability of the empty set? That's 0. That's definitely not the product of even number and odd number, right? Probability that you'll get an even number is half. Probability that you get an odd number is half. Half into half is 1 by 4. That's the probability of the product P of A into P of B. That's not a probability. That's the product of the two probabilities. On the other hand, the probability of the intersection, the number being both even and odd, is 0. Right? So it doesn't happen. Okay. So here's a point to remember, don't forget this. If two events are disjoint, then actually they are not independent at all. Why is that? Because if they are disjoint, and if I tell you B happened, then A did not happen. You know that for sure, right? So the occurrence of B definitely affects the conditional probability of A. Okay, so that's important to know. So here's the sort of the last point here is sort of a bit counterintuitive. Maybe it's a little bit surprising, but it's a very crucial part of independence. Independence does not mean disjointness. Okay, so they have to have two events if they're independent. They have to have a non-trivial intersection. The intersection should be possible. A and B must be possible for A and B to be independent. Okay. Small idea, but important to keep in mind. Okay, here's another example. I'm going to modify this event B slightly. A is still the even number 2, 4, 6. I'm going to make B as a multiple of 3. Okay, B is the event that the number that showed up is a multiple of 3. A is the event that the number that showed up is 2, 4, 6, even number. Okay, you go through the mechanics of the definition. A intersect B is just 6 alone. Probability of A intersect B is 1 by 6. That's clearly 1 by 2 into 1 by 3. That's P of A into P of B. Okay, so the definition holds. So A and B are independent. The event that you get an even number is independent of the event that you get a multiple of 3. Okay. So I've seen students get confused by this. So first confusion is A and B have an intersection, how can they be independent? Okay, but this is what I'm trying to dispel here. Intersection is mandatory for independence. Without intersection, there's no independence. Okay, it seems a bit it's sort of against our normal English understanding of independence. Independence, the two people are away from each other. Okay, so with here it shows there is an intersection and still there is independence. So only when there is an intersection there can be independence. Okay. It's a sort of a different understanding of what it is. Okay. The other slightly interesting doubt I've had students ask me over a long period of time is the die is being thrown only once. There's only one number, and what is this meaning of two events defined from there and two events being independent, etc. Okay. I want you to think about that on your own and be convinced that there's no problem there, right? The outcome is only one. The experiment is done once and there's one outcome. There are so many events that are defined in that sample space, and your outcome can belong to multiple events. It can be favorable to multiple events. All of that is perfectly fine. It's okay. It's not wrong. Okay, don't be confused by that. Okay, that's one more example to sort of clear up the air. So to drive home this point, I'm going to repeat it once again. Okay, the same point in another setting, because this is important enough that you should have a good deep understanding of it. Supposing you draw a card from a pack, I'm going to define an event A as the card is a spade, event B is card is a king, and A intersect B is what? There is an intersection, right? Card is a spade king, right? There is a spade, and this is card, king is also there, the spade king. So probability of A intersect B is 1 by 52, that's 1 by 4 into 1 by 13. And right away you see that's equal to P of A into P of B, right? Probability the card is a spade is 1 by 4, right? There are 4 suits, all of them equally likely in some sense. Card is a king, there are 4 kings, 1 by 13 is the probability. So you see A and B are independent. So when you have a pack of cards, you're drawing a card, the event that the card is a spade has no influence on the probability of the card being a king. Okay, the card being a king before you knew it was a spade, and card being a king after you knew it was a spade is exactly the same, doesn't change. Okay. Once again, I've repeated the 2 points of confusion. There is an intersection, there is a spade king, how can it be independent? In fact, because there is a spade king, it's independent. If it's not, there wouldn't have been independent, right? Very important. And there's only one card drawn. What is the meaning of two events? And remember that that's how probability spaces and events are defined. There's only one outcome. The outcome can belong to multiple events, it can be favorable to multiple events. Okay, keep that in mind. Okay, so we've seen independence of two events. Okay, it turns out one can define independence for multiple events. Okay, now this definition has a lot of other motivations and important reasons why, but I'm going to just make this definition and sort of drive home the important peculiarity about this definition. Okay, so if you have three events A, B, C, you have these conditions for A and B being independent, A and C being independent, B and C being independent. Those three are easy to write down. I've written them down first. Okay, you can see that's what I've written them down as. Let me just pick up this laser pointer, it's a little bit better. You have P of A intersect B being P of A into P of B. A intersect C being P of A into P of C, B intersect C being P of B into P of C. So, mutual independence of three events does not stop there. There is one more condition that is required. Here is this important condition. P of A given B, A intersect B intersect C has to be the product of 3. Only then you see all 3 are mutually independent. Okay. So, the first condition is called pairwise independence. Okay. Only 2 at a time they are independent. The third condition makes them really mutually independent. The 3 events are mutually independent. Okay. Now, it is possible, I have given an example here of 3 events in a very simple sample space, tossing a coin twice, which are pairwise independent but not mutually independent. This is possible. Okay. So, here is A, B, C, I have just defined them as subsets, and A and B, A and C, B and C are independent pairwise. You can check that out. I will leave you to check this, but this condition is not satisfied. A intersect B intersect C is 1 by 4, and that is not the product of 3 probabilities. So, it may happen that pairwise independence is true, but mutual independence is not there. Okay. So, this is at this point we will leave it as definition, but the way I usually think of this mutual independence of a bunch of events is, once you have A, B, C being independent, any intersection that you can think of always becomes a product. Okay. So, the multiplication rule is sort of like the motivational point behind this, right. So, any intersection you do becomes a product. Okay. So, that is nice to know. You can push this to multiple events as well. Okay. Why stop at 3? You had, you had 2 events, we define independence for them, 3 events, we define independence. You can define for any number of events. If you have n events A1 to An and they are said to be mutually independent, if for every collection of subsets of these events, right, you pick I1 to Ik and you look at AI1, AI2, Aik. You pick any subset A1, A2, A3, A2, A10, A15, A1, A100, A11, whatever, any subset. You can take subsets of size 3, subsets of size 4, 5, 6, 7, everything. Okay. For any subset of these n events, the probability of their intersection has to be equal to the product of the probabilities of the individual events involved in this intersection. Okay. P of AI1 intersect AI2, so on till intersect Aik is probability of AI1 times probability of AI2, so on till probability of Aik. Okay. So, this is the condition. Okay. When the probability of events satisfy this condition, they are said to be mutually independent. Okay. So, there are a lot of constraints here, the 2 to the n constraints. If you think about it, maybe little bit lesser than that, but so a lot of constraints. So, there's a whole bunch of things to check. Okay. But here's an interesting result. I want to point this out. I won't go into depth of proving these things and all that. There is a proof here. I won't describe that. So, if A and B are independent, it turns out A and B complement are also independent. This you can prove. Okay. You don't have to check this. If somebody tells you A and B are independent, it implies that A and B complement are independent. So that's sort of intuitive in some sense. Think about why that's true. So, B does not affect A, so B complement should not affect A as well. So you can so basically this result says if 2 events are independent, complement of one event and the other event together are independent. So, you can use this rule twice and simply get to the point where A and B are independent implies A complement and B complement are also independent. So notice how powerful this independence is. It's a really powerful definition. Seems very simple, but implies so many other things. Okay, right? Even if you complement, either complement or not complement, they are all independent. Okay. This in fact extends to n events being mutually independent as well. Okay. Any subset, any collection, sub-collection of these events, you take a sub-collection and then either complement or not complement. Okay. So, you do whatever you want there, those guys are all independent. Okay. So, for instance, if A1 to A100 are mutually independent, A1 and A80 complement are independent. A1, A80 complement and A50 are mutually independent. Okay. Any subset with complement, without complement, they are all mutually independent. Okay. So, that is the power of this result. It is very, very powerful. So, once you know they are mutually independent, you can just multiply. Okay. The rule of multiplication works for any intersection of these events. Okay. So, that is the power of this definition, and it is put to use quite a bit everywhere. So, in physically you may get independence quite easily. Events involving different things are going to be independent and you can just multiply. Okay. The rule of multiplication really helps you there. So, that is how independence is usually used in practice. You know that the events are coming from physically independent experiments in some sense, realities in some sense, so you can multiply the probability. So let me show you a problem which seems simple, but you can use independence and very easily solve it. Okay. So here's a problem. There will be more problems of this nature in your assignments, but let me do one for you in some detail. Okay. Here's the situation. There are 3 cities, let's say cities or towns A, B and C. There are 2 parallel roads that connect A and B. Okay. There are 2 roads, one road connects A and B, another road connects A and B also. Same way between B and C, there are 2 parallel roads. Okay. Right. Hopefully situation is clear. So what people have observed is each of these roads can get blocked with the probability P, and that's independent of all the other roads. Okay, so here's a mutually independent scenario. What is the event? There are 4 events here. First road from A to B gets blocked, second road from A to B gets blocked, first road from B to C gets blocked, second road from B to C gets blocked. These are the 4 events, and the problem says these 4 are mutually independent and each happens with a probability P. So now you know any sort of intersection with this or the event complement, what can you do? You can just multiply. Okay, that's the beauty of this, right? So, and you know this is reasonable because you know maybe reasonable, I think. So you have each of these roads having different physical characterizations. You know, so something that happens this road may not affect what happens in the other road. So it's reasonable to assume. Okay. Now you've been asked to calculate a certain probability here. So I may or may not do this entirely, but let's see where we go with this problem. So in this probability space, we need to compute a certain particular probability. Let's see what that calculation works out to. Okay. So the question is asking a conditional probability, even though the word conditional is not there. It says what is the probability that there is an open route from A to B, given that there is no open route from A to C. Okay. So let's see if we can calculate this probability. Okay. So what is an open route from A to B? Right. If there is an open route from A to B, it means either first road or the second road should be open, isn't it? So let's see if there is some calculation that's possible here. So let's first calculate probability of open route from A to B. This is the probability that I'll call this 1, 2, 3, 4. Okay. 1 is open or 2 is open, isn't it? So probability P is the probability that the road gets blocked. What's the probability that the road is open? That's 1 minus P, isn't it? Okay. So 1 is open or 2 is open. So this seems a little bit difficult to do. So what one can do here is maybe, you know, find the other way around. So you can do this. Maybe I'll write it like this. You'll see the various ways to do this. I'll do it like this. Probability that there's no open route from A to B. This is actually easy to calculate, right? So 1 is open or 2 is open. It seems very hard, but this is easy to calculate. 1 is blocked and 2 is blocked, right? Notice how is this working out? So this is a trick that you should use in every probability calculation. You see a probability and you see that it's hard to evaluate. What do? You go try to find its complement. Okay. Probability of open route from A to B, I try to find the complement of that probability of no open route from A to B. And you notice here that this becomes very easy. What is this? 1 is blocked, 2 is blocked. These 2 are independent events and I am doing AND. If you do independent events and you are doing AND, you can multiply. That's just P into P and you get P squared. Okay, notice how this worked out very, very easily. So this will become 1 minus P squared. Seems easy enough, right? This is the probability of an open route from A to B. Okay. So I have to find a conditional probability here. This seems like a interesting enough. So what's the probability of having no open route from A to C? Okay, that's the question that's been asked, right? What's the probability you do not have an open route from A to C, and then you want a condition on there is an open route from A to B. Okay, so let's do this conditioning, right? So probability of no open route from A to C given open route from A to B times probability of open route from A to B plus the other possibility, right? So no open route from, let me call this event as E, okay, just to simplify my matters here, writing here probability of E given the open route from A to B, I will call this event as F, okay, E given F complement times probability of F complement. Okay. So now if there is no open route from A to B, what is the probability that there is no open route from A to C? That's 1, isn't it? Do you agree? Okay. If already there is no open route from A to B, probability that there is no open route from A to C is just 1. You don't care. Whatever happens between B and C, there is no open route from A to C. It's finished, right? So that's 1. And this guy we know already, right? What's the probability that there is no open route from A to B? That's P squared. Okay. Now what's the probability that there is an open route from A to B? This we have also calculated, 1 minus P squared. And what is this guy? What is the probability that there is no open route from A to C given that there is an open route from A to B? There should be no open route between B and C, okay, and that's the same as no open route between A and B. So that will end up being P squared. Is that correct? So this will end up being P squared. Okay. So you get here, you multiply P squared 1 minus P squared plus P squared, you get 2 P squared minus P power 4. Okay, so that's the probability that there is no open route from A to C. That's E. Okay. What you have to find is P of F given E, isn't it? That's going to be P of E given F times P of F by P of E, and you know all these quantities, right? So what's probability of E given F? That's just P squared, right? What's probability of F? That's 1 minus P squared, okay? Here it's 2P squared minus P power 4. You substitute all this, so this guy is P squared, so I'm sort of running out of room. Let me see if I can squeeze this in. 2 minus P squared, oh no, 1 minus P squared, sorry, divided by 2P squared minus P power 4. So you get the final answer, right? Maybe you can cancel the P squared, and this guy ends up being 1 minus P squared by 2 minus P squared. Okay, so this is your final answer. So you can see how we argued this out. Maybe the mechanics of it is a little bit, maybe I wrote it in a bit of a painful way. Hopefully you can see, you can write events very carefully and argue about them very carefully, and notice how this independence was helping you, right? So when you want to do AND two things with independence, you can just multiply, and that's very smooth and easy to do. And you can just repeat this calculation, multiply them together, and then you use Bayes rule, total probability over and over again, you will get your answer. Okay, I think to me this problem is very interesting and simple, and at the same time conveys a lot of ideas. It brings all that we discussed in this area of conditional probability, law of total probability, Bayes theorem and independence together. Okay, so it's a very nice problem. I want you to think about this and get your comfort level with this problem going quite a bit. Okay, so it uses there's just 4 simple basic events, each of these roads getting blocked, and they're all connected in one way and they're all independent, right? So each is with P, and then there is this question that's asked about open routes, conditional probabilities of open routes and no open routes, and look at the way we have to calculate, right? So you have to think about how to organize an event, and notice this very subtle thing of how the union is, when the union is difficult to calculate, you just go to the other rules, right? So P of A plus P of B minus P of A intersect B, right? So or the other way around. So many ways to do these problems, and you can go to the, if you don't like the probability of an event, you can find the complement of the event and then do 1 minus. All of these are very interesting, important tricks, and as you go along, you have to pick up these tricks and be comfortable with solving problems. So this problem is very interesting. Hopefully there will be more problems like this in the graded assignment and practice assignments, and you can improve with practice. Okay, that's the end of this lecture. Thank you very much.